Tell me how you'd start it. Okay, so tell me what that looks like. All right, now, this is a z-score. Now, in order to write an equation, we have to make it equal to another z-score. So we've taken this and made it into a z-score. What is this? Is that a z-score? Exactly. And see, what's important to remember is that this is the probability. I need to change it into a z-score. So tell me about this picture. If I made it, and it kind of looks like this, all right? Now, my number, 1056, is on this side of the mean. How do I know it? Exactly. Okay? So I know that it's bigger, I know that it's smaller than the mean, right? Now, if I convert this, now I don't know what the mean is, but if I convert this to a z-score, the mean will become 0, and will this number here be positive or negative? Now, how can I find out this number as a z-score? Yeah, how would you use the calculator? Exactly. In the inverse, keep in mind that what happens is number 2, that's when we're finding a probability. In this case, we have a probability. What we want to do is convert it to a z-score. But the other thing is, what you got to remember is whether you're using tables or the inverse normal, that you put in an area and it's going to give you the number right above it. So the problem is that if I put in 0.6, it's going to give me this number right here. Does that make sense? If I go to inverse normal and I put in 0.6, that'll give me this number right here. Now, that's not the end of the world, but what I could do is, if there's 0.6 over here, how much is over here? Now, put that in the inverse normal. Say it again, negative what? What's after the 5? We'll do that, okay? All right, now, put in the 0.6 and tell me what you get. Exactly, okay? So my point is, you can do this and switch it to the 0.4 and get the actual number, or you could put in the 0.6, but you just need to realize if you put in the 0.6, that it's going to give you the positive version of that number. That's why I'm saying you have to figure out whether this is positive or negative. Does that make sense? All right, so now I'm going to make an equation out of that. I'm going to multiply this times this. Okay, now we're going to do the exact same thing with the other one. So what's that look like? All right, so now we've got to take this. So let's do the same kind of thing. What I need to do then is I need to figure out 0.55 is below it. So is my number above the mean or below the mean? So what I'm going to say is I'm going to say this is the mean, and I'm going to say this is my number right here. All right? Now, if I put in 0.55 into the inverse normal, it'll give me this z-score. And see, once I have that, then I'm going to put that right here. So tell me what happens when you get that. Zero 0.125666. We'll just get a couple sixes. I'll make it 67. Okay? Now, I'm going to do the same thing to this. All right. Now I've got two equations. What am I going to do? Yeah. Now what I'm going to do before I rewrite it is I'm going to multiply one of them by -1. Do you notice how they both have a minus mu? What I'm going to do is I'm going to multiply this one times -1, making it minus 1080, making this plus, and then making this minus. And see now, like you say, when I add straight down, these mu's equal 0. So what's 1056 minus 1080? -24. And then what's negative 0.025 blah, blah, blah minus, or add them together if you will. It's going to be negative. Say it one more time. Negative what? All right. Now, how do I find the standard deviation? Exactly. So, but they're both negative. So if you want, just do in your calculator, do 24 divided by 0.12724. 18 point what? All right. Now, how do I find the mean? And see, here's what I suggest. Do you see how the mean is positive in this one? Now, do you still have the 18.861 in your calculator? Now, times it times this. Negative 0.12567. All right, now that's you multiplying those two together. Now what do I got to do to get the mean by itself? Add 1080 to it. So this now push plus 1080. All right. So the key here is what happens is this kind of question is pretty common. What you've got to be careful about is whether or not your z-score is positive or whether it's negative. Other than that, whenever I've seen this in all these different versions, the other part works pretty much the same. Where they get different is sometimes both of the z-scores are positive, sometimes both of the scores are negative, sometimes one's positive and one's negative, and you got to know, you got to be able to figure it out. Does that make sense? But after that, then we're just like you say, solving two equations simultaneously. Now, today what I want to talk about is the remediation for that last test. Now, let's get this a little bigger. All right, take a look at this. It says a fair three-sided die has got numbers 1, 2, and 3. Now this could be a dice, it could be a spinner, it could be any number of things where the numbers all have an equal chance of happening, okay? And then there's a five-sided die, or again, it could be a five-sided spinner. It will all work the same way. Now, for each die, the number facing up is noted. So the random number x is the larger of the two numbers if they're different, and then the common value if they're the same. So what they want us to do first is figure out how the probability of x equaling 3 is. Now again, x is the larger of the two numbers if they're different, and then the common if they're the same. How can we figure out the different possibilities? Yeah, exactly. So let's say 1, 1, 2, 2, 3. That's this five-sided thing, okay? And then let's go down and we'll do 1, 2, 3. Now in this case, what I would do is I would write both numbers. Or actually I'd write the x, because that's all we're really doing, right? So if these two numbers come up, what's the large? Which one? What's the number I'm going to use? If the first dice is a 1 and the second dice is a 1, which number do I pick? Because it's the same, right? If they have a common value, then it's the same. All right, now, oops, hang on. Oh, so that would be the same thing for this next one, right? Now, what if I rolled a 1 and a 2? What number do I get? No. Remember, the x is the larger of the two numbers. It doesn't say to add them together. So if I roll a 1 and a 2, what number do I get? What are the two numbers I just rolled? Exactly. Okay? All right, so now look at here, same thing. This is also going to be a 2, right? This is me getting a 1 and a 2. Now this is me getting a 1 and a 3. What number do I keep? And see, now it's a 2 and a 1. So what number do I keep? And then 2 and a 1, 2 and a 2, 2 and a 2, and then a 2 and a 3. What number goes here? Do you see what's going on? When you fill out this chart, think about what the number, this is one thing, and this is the other. Sometimes what will happen is that they'll have like two dice, and they'll be both six-sided dice, but they'll say the first one is even, and the second one is odd, or something like that. Well, in the case then, you just got to label one of them. This is the first, and this is the second. Do you see what I'm talking about? But in this case, we can tell which one's which because one of them has different number sides than the other, okay? So here, if I get a 3 and a 1, what number do I keep? And if I do a 3 and a 1, again, I get a 3. What about a 3 and a 2? 3, 3 and a 2, 3, and then a 3 and a 3. Right? Now, how many possible things do I have? And how many of them are 3? 1, 2, 3, 4, 5, 6, 7. This right here is a method for showing the probability is 3 or 7 over 5. Or 7 over 15. Does that make sense? Now, there are other ways to do this, but this is perfectly fine as far as a method. No, yeah, right. Okay, and the thing is, we've had situations where we have had to add them before. And I don't know that you've run across one like this, okay? Now, I'm going to do the same thing now. I'm going to set up a probability distribution table, okay? So what happens is there's going to be an x, and then the probability that my random variable x is equal to that little x. Now, what are the possible things my x could be? 1, 2, or 3. There's the only things can happen because I'm looking at every possibility up there, right? Now, what's the probability that it gets to be a 1? And what's the probability that it's a 2? And then what we already know what's about pi over 3. It's 7 out of 15. And how do I double check it? 2 plus 6 is 8. 8 plus 7. All together, those equal 15 over 15. These probabilities have to add up to 1. All right, does that make sense? Okay, so now, I'm going to scooch it up just a little bit. Now, this is the probability distribution table, and they want me to find, given this probability, because you notice how this is the capital X, it's referring to this table. So what's the probability that X is greater than or equal to 1? How about this? What's the probability that X is 2? What's the probability that X is equal to 2? What if I said, what's the probability that X is greater than or equal to 2? Because you would add these two together, right? What if I said, what's the probability of X being greater than 2? Because that's the only one, right? Now look at this one. What's the probability of being greater than or equal to 1? It's this plus this plus this, which is equal to 1. It's 100% chance that my random variable will be 1 or bigger than 1, because they're the only possibilities are 1, 2, or 3. Does that make sense? Okay, so now let's take a look at this next one. If you've got a probability distribution table, we'll make it so we can still see it. How do we find the expected value? I take each x times its probability and I add them all up. Okay? In a probability distribution table, it's the sum of all the x's times their probabilities. That's how I find the expected value. Okay? Now, how do I find the variance? So the variance is going to be, it's going to look pretty much the same way, only it's going to be 1 squared. And see, the thing is, if you have this in your calculator, then you can go and, well, do me a favor, figure this out for me. Tell me what this is going to be. Um, 2 over 15 plus 12 over 15 plus 21 over 15. Yeah, don't multiply. Go back and just change them to pluses. Don't erase it. Just go back and change them to pluses. Seven over 3. Okay? Now, this is still in your calculator, right? You could go in there now and change it to 1 squared, 2 squared, and 3 squared, which is like we have down here, right? What's that going to be? All right, but the thing is, that's not all I got to do. What else do I got to do to find the variance? I got to subtract the expected value squared. So what do you get when you do that? Exactly. That's the variance. Okay? The expected value is each x times its probability, and you add them up. The variance, you go back and then you change those to squares, but then you have to subtract the expected value squared. And the thing is that you have to write this down so they can see what method you're using. On this one, I think this was worth 1 point. Then this one was worth a method point. And then the final answer was worth a point. All right, questions about that? All right. Now, tell me about this one. It says that on a given day, the probability that Jake brings his lunch is 0.72. Jake brings his lunch on Monday. What's the probability that the next time he brings his lunch is on Thursday? Now remember, this test was on 3 things: permutations, combinations, it was over binomial distributions, and geometric distributions. Which one are we looking at here? Or how about this? What's a geometric distribution and what's a binomial distribution? How can I tell the difference? Or what do you know about those 2 things? Okay, so binomial, again, 2 outcomes. All right, both of them, 2 outcomes, right? And then P is constant, okay? And then independent trials. However, a binomial has a fixed number of trials. In a geometric distribution, theoretically, it could go on forever. Because what are we interested in a geometric distribution? The first time we have a success, okay? In a binomial distribution, we're looking at, out of these trials, how many of them were successful. Okay, so which one of these situations are we talking about here in number 2? Why do you think that? Exactly. We don't know. And see, the thing is, think about this. What's this 0.72? And so that's our probability of success, right? Okay. Now, it says, what's the probability that the next time he brings his lunch is on Thursday? So you notice how I only want to know about one success. Okay? So, what does that look like? It's Monday. brought my lunch. Okay, that's a given, right? Now, Tuesday, Wednesday, and Thursday, right? Okay, now, what happens on Tuesday? Do I bring my lunch or not in this scenario? When's the next time I bring my lunch? So, did I bring it on Tuesday then? So, what's the probability of that happening? Right, what's that? All right. There we are, not bringing my lunch. What happened on Wednesday? Not bringing my lunch. What happened on Thursday? Brought my lunch. Okay? Now, you could figure it out this way. What's this times this times this? Okay? I guess it looks better like this. Or the formula. Do you remember the formula for a geometric distribution? All right, so remember, in this case, this Monday is irrelevant. Because here's when the trials come. See this Monday? It doesn't count because we definitely brought our lunch. Tuesday's a trial. Do I bring my lunch or not? Wednesday's a trial. Do I bring my lunch or not? Thursday's a trial. Do I bring my lunch or not? If I want to find the probability that x is equal to 3, then what I'm going to do is that I'm going to have two failures. It's going to be the probability of failure, and it'll always be one less than this number. Because my first success happens on the third try, that means I have to have one minus that failures. That's this failure, and that's this failure. Happened twice, right? Then I'm going to multiply that times one success. That's this one right here. So what we're looking at really is the formula. 1 minus p, and see 3 minus 1, that's going to be to the second. Well, that's the same thing as 0.28 times 0.28, right? So there's a couple different ways to look at it, but keep in mind, the first trick is identifying that this is a geometric distribution, and then the other thing is identifying what the trials were. When people mess this question up, a lot of them got confused about this Monday. Monday's not a trial. This is a trial because we don't know. Did it happen Monday? Did it happen Tuesday? Wednesday? Thursday? Monday, we know exactly what happened. It's not a trial. Does that make sense? All right. You got any questions about that? Right. See, a lot of people did that because that's, like I said, it seems like the probability of bring my lunch. But keep in mind, in this case, it has to happen if the first time I bring it is on Thursday, that means I didn't bring it here and here. And so I have to include those probabilities. Does that make sense? Now, if I asked you, what's the probability of bringing your lunch on the next day? Well, now that's 0.72. If Monday I brought my lunch and I want to know the probability of bringing it again on Tuesday, that's 0.72. Does that make sense? But if it's on Thursday, I also have to consider what happened on Tuesday or Wednesday first. All right? Now, tell me about B. B says find the probability that for 12 randomly selected days, Jake brings his lunch no more than 9 days. So first, are we talking about binomial or geometric? Why do we know that? Exactly. Notice in this first part, it doesn't tell you how many days that we actually go. The fact that they talk about this 3, it lets you know that that's what I'm looking for, not that we had a certain number of trials. All right? So now the probability of success is still going to be the same. And how do I write this? No more than 9 days. The probability that X is what? Less than or equal to 9. Now, how many trials are there? So that means I have to figure out the probability of X equaling 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Is that true? Or I can do 1 minus the probability of X equaling 10 and 11 and 12. Which one do you want to do? So, how do I figure out this, 10, 11, and 12? So what do I write? Which is, and how many am I choosing? And then what comes next? Because that's the probability of success. All right. Now, what's the exponent? Again, because think about it. I want to have 10 successes. So that's 0.72 times to the 10th power. 0.72 times 0.72 times all the way 10 times. Does that make sense? So then how many failures must I have had? Because I have to have 12 altogether, right? Then what do I do? See, now I'm going to have 11 successes and only 1 failure. And then what am I going to do? And see, in this case, I could even leave out this and this because they both equal 1, right? All right, but it doesn't make a difference because I'm going to do this in the calculator. Where do I go in the calculator to find these 3 numbers? So, push menu, and then number 7. Do you see where it says distribution? All right, now push enter, and do you see where it says normal PD and normal CD, and then inverse normal, and then number 4, binomial PD? That's what you want, number 4. Because we're doing a binomial distribution, all right? Now, you want a list, so do number 1. Okay, now what are our x's? So enter, do 10, enter, and then 11 or equal, and then 12 equal. After you get those 3 numbers in, just press that equal. Now, what's the number of trials? And then what's the probability of success? And see, if you put those in, now you press enter, equal again, and then you're going to get all 3 of those numbers. Now, if you slide over, what's the first number? And the thing is, you see how they've got 4 digits? That's going to be fine in most cases. I'm going to give an extra one just to be safe. What's the next one? And see, here's the example. Do you see how this first number is a 0? I really need to go 1, 2, 3, 4, and then a 5th spot. So it's going to be 7. Does that make sense? It's not that big a deal for this one, but definitely for this one. And then what about the 12? What's that one going to be? And so if you want, I would just put a 0, 8. It doesn't have to be all the same. Okay? Now, I'm going to add all those up, and then I'm going to subtract them from 1. Because remember, what we just figured out is the probability of exactly what they didn't want to know. We just figured out the probability of it being more than 9 days. They want to know no more than 9 days. So we find this probability, but then we take it away from 1, and that's their probability. This is really common where if there's 10, 11, 12 trials, they'll pick one end, and it'll make it look like you got to do like 8 or 9 of them or 10 of them. And they never expect you to do that. It's much easier to just do the 2 or 3 and then subtract it from 1. Does that make sense? Any questions about that? Go ahead and look, see if you can find it. What page was it? I'm sorry, what page was it? Yeah, 217. All right. So this is similar. However, in this case, let me write this down. What number was this now? 16? All right. Now, what is the probability of success? In part B, oh, wait a minute. Okay. All right. So in part A, you found the mass of the randomly selected pie is less than 425. What did you find in part A? All right, 0.659. That's the probability of success, yes? Now, in part B, you did the probability that x equals 4, right? So you did 4 choose 4 times 0.659 to the 4th, and then whatever this minus 1 is to the 0, right? All right, now part C, it says exactly 7 out of 10. So what's my number of trials in this case? What I want to know is the probability that x is equal to 10. Not greater than and not less than, exactly 7 out of 10. So that would look like this. Whoops, 10 trials, 7. Hang on, back up. 7 of them are successes, and then 3 of them are failures. Is that what you did? So again, do you see how this says no more than 9 days? Well, that's why we're getting this thing where it's an inequality, less than or equal to 9. Okay? In 16b, it says that 4 out of 4 are less than that, right? So that's why we did 4 out of 4. This is the probability that x equals 4. In part C, they say 7 out of 10. Now, it's not saying 7, 8, 9, and 10. It's saying 7 out of 10. So this is the probability that x equals 7. I wrote the wrong thing. Okay? So that, that doesn't mean that you want to go and do 8, 9, and 10. It just means that there are exactly 7 of them out of the 10 that, in this case, are successful, meet our criteria. You good on that? All right. So tell me about number 3. The probability that Janice will buy an item online on any given week is 0.35. Janice does not buy more than 1 item a week in any week. The probability that Janice buys at least 1 item online in a period of n weeks is greater than 0.99. Find the possible values for n. Do you remember how to do this? Yeah, but we got to get there first. So let's do this. Change this. At least 1 item in n weeks is greater than 0.99. How do I write that as a probability statement? Find the probability that she buys at least 1 item in n weeks. It's the probability of what? So the probability that Janice buys at least 1 item. Give me the examples of at least 1 item. What's the smallest number of items it could be? At least 1? Do you see what I'm talking about? At least 1, the smallest one could be a 1, right? And then what other could it be more than that? Could it be a 2? Is 2 at least 1? Is 3 at least 1? Is 4 at least 1? So at the end of the day, this means greater than or equal to 1. Does that make sense? At least 1 means greater than or equal to 1. It could be any number bigger than 1, and it could be 1, but that's as low as it could go. Okay? Now, the problem is I don't know the number of trials. So there's no way for me to do this because I don't know the number of trials. I don't know how far to go up to because I can't go the probability of 1, 2, 3, 4, 5, 6 and add them up. I can't do it. Now, this is the same thing as 1 minus the probability that x equals 0. Does that make sense? Okay? 1 minus the probability of x equals 0 is the same thing as the probability of x being greater than or equal to 1. Now, we know that this probability is greater than 0.99. Right? All right. Now, what's the probability of it would be going? Well, here, let's do this. Can I get this probability by itself? How do I get rid of the 1? So what's 0.99 minus 1? Minus 1? All right, now I'm going to divide both sides by -1 or multiply both sides by -1. This is going to become positive and this is going to become positive, right? However, when I divide or multiply both sides of an inequality, I have to switch the sign. So now it's going to be less than. Yep? All right, now, how do I figure out the probability? How many trials are there? And how many of them am I talking about? 0, right? Now, what's my probability of success? 0.35. And that's to the 0 power. And then 0.65. And that's going to be to what power? Not to 0. Because, right? Now, this is going to be great or less than. It's going to be less than. Wait a minute. Yeah, it said less than, right? Less than 0.01. Now, n choose 0 is 1. 0.35 to the 0 is 1. So this is what I end up with. Now, how do I write it as a logarithm? So what's the base? And that goes down low. And what did I end up with? And it's still, and see now, what happens is it just switches it around. A logarithm is the base times this power is equal to this number. And do you see that's exactly what this says? 0.65 to this power is equal to that number. So then all I can do is figure out what log base 0.65 of 0.01 is. What's that going to be? So now this says 10.69 is less than n. Now I can reverse it and say s or n is greater than 10.69. I can, whatever, what's my answer? Keep in mind it's a number of trials because it can't be 10.69. It's either going to be 10 or 11. Which one is it? Because it's got to be greater than, right? So n equals 11. Okay? Now take a look at number 4. Here it says Freddie has got 6 toy cars and 3 toy buses. This is important and people miss this. They're all different. Okay? He chooses. So that means, are we doing arrangements or combinations? 4 toys to take with him. How many different ways can he choose the toys? How many toys does he have? And how many is he choosing? 9 choose 4. Okay? So there's no, the fact that there's toys and cars, it doesn't make a difference because in this problem, they don't care. They're just talking about the number of toys. Okay? Now, part B, it says how many of these choices will include his favorite car and his favorite bus. All right, so we're going to say that we've got 4 choices. And this one is his favorite bus. We'll call him bus number 1. And this one is his favorite car. We'll call it car number 1. Okay? Now, how many toys are left? There are 7 left. And how many can I choose from? or 2. I'm only choosing 2, right? So this is going to be, now, there's only one way for this to happen and one way for this to happen. So it's going to be 7 choose 2, or 21 ways. Does that make sense? All right? Because in all my selections, there's going to be this favorite toy and this favorite toy. So the only thing that's going to ever change are these other 2 slots, and that's what I have to figure out. Okay? Now, what about the C here? It says that Freddie arranges the 9 cars in a line. Find the number of possible arrangements if all the buses are next to each other. All right, so we've got bus, bus, bus. And we've got car, 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 car. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Right? How do I do this? All right, there are my 3 buses. I consider them all one thing. So now, how many things am I going to arrange? So I'm arranging 7 things. Are any of them identical? So how do I do that? Yep, 7 factorial. Okay? 7 factorial. Now, then what do I got to do? Because see, that's taking these buses in this order. 1, 2, and 3. Always in this order. 1, 2, and 3. And moving them around. They could be here. They could be here. These cars switch places. They could be here. They could be here. There's 7 factorial ways that these 3 buses in this order can be arranged. So then the other thing I can consider is how many different ways can my buses be arranged? How many buses are there? So how many ways can my 3 buses be arranged? Okay? Whenever you're doing things that are together, take the group that's together and count them as one thing. And then find out the number of ways they can be arranged. My one group can be arranged in 3 factorial ways. All right? Then multiply that times the number of ways all of the things, in this case, 7 things can be arranged. And again, there's no duplicates, so it's just going to be 7 factorial times 3 factorial, which ends up being something like 3,240. Okay? Well, what do you mean placing? There's choosing and arranging. Which one are we doing here? Exactly. Oh, you mean this? Where I go 7p3? Because what happens is I only use this when I have 7 things, but I'm only arranging 3 of them. How many buses do I have? And I'm arranging all of them, right? That's 3 factorial. If you will, that's 3p3. 3p3 is the same thing as 3 factorial. I've got 3 things, I'm arranging all 3 of them. All right? Does that make sense? Now, even in this case, where I have this 1, 2, 3, 4, 5, 6, 7 things, if I count this as 7 things, I'm arranging all, because remember, this is just one thing. This is a bag, right? Okay? So I'm arranging all 7 things. That's why it's 7 factorial. You could do 7p7, but that's going to give you the same thing as 7 factorial. The only time I use this is when I'm arranging, I have more things than I'm actually arranging. Does that make sense? So then take a look at D. And D says, find the number of possible arrangements if there are no buses together. All right, so what's the first thing we do here? So not the buses. What's separating the buses? So if you want, we can go like this. C1, C2, C3, C4, C5, and C6. There are my 6 cars. Now, for the buses to be separated, where could they possibly go? They can go in any of these spots. Okay? Now, the first thing I do is I figure out how many different ways I can arrange my cars. How many different ways can I arrange my cars? How many cars are there? So that's going to be 6 factorial. And in this case, they're all unique, so I don't have to worry about dividing by anything because they're all different. Okay? Now, in this case, I've got 1, 2, 3, 4, 5, 6, 7 spots to put buses. But how many buses do I have? This is one. Do you see how I've got 7 places to put buses, but I've only got 3 buses? Does that make sense? If you will, I've got 7 stars. Or if you want, we could say they're buses. But I'm only going to arrange 3 of them. Because that's all I got. Does that make sense? All right, now once again, because the buses are all unique, I don't have to worry about dividing by anything factorial to take that into account. Okay? All right, what about number 5? It says, Sean has got 6 apples and 2 pears. He chooses 4 of these fruits at random. The random variable x represents the number of apples he chooses. Show the probability he chooses exactly 2 apples is 3 over 14. How can I find the probability that he chooses? Now again, how many is he choosing? All right. Now, what's the probability that 2 of those 4 are apples? How can I go about doing this? Wait a minute, because remember, I've got how many apples? So I could do 6, choose 2. Those are my apples, right? All right, but I've got 6 of them, and I'm only choosing 2 of them. Now, how many pears am I choosing? Right? Now, that tells me the number of ways that I can choose 2 apples and 2 pears. What do I have to divide by? 4, choose 2. How many pieces of fruit do I have? Exactly. Now, do you notice how these 2 numbers add up to this number? And these 2 numbers add up to this number? That always is going to be, okay? Now try it. Tell me what 6 choose 2 times 2 times 2 over 8 choose 4 is going to equal. So 3 out of 14. All right, now we're going to make a probability distribution table, right? Is it possible to only choose one apple? It's not. And see, I can try it, but then what happens is that I have to have 3 pairs, but I don't have 3 pairs, do I? So that's not going to work. So I go the other direction. Is it possible for me to choose 3 apples? Then how many pairs am I going to choose? And I'm still going to divide by 8, choose 4. Now that's still in your calculator. Just change these numbers to 3 and 1. So that's 4 out of 7 or 8 out of 14, right? Now, is it possible to choose 4 apples? If I do, how many pairs am I going to choose? All right, now I've got everything I need for my probability distribution table. I put a little x, and what are the possible things that could happen? How many apples could I draw? 3 or 4, right? And what are my probabilities of each one happening? Now, if I add 3 plus 3 is 6, 6 plus 8 is 14, my probabilities add up to 1. I like that, right? So that's how we figure out this. Questions about that? Because remember, when I do when I find a probability, it's the thing I'm interested in. All right. This is the number of things I'm interested in. This is me getting 2 apples and 2 pears. That gives me a total of 4 fruit, but 2 of them are apples. Okay. So this gives me the number of ways that's going to happen. But then I have to divide by the number of ways to pick with no restrictions. So in this case, if there's no restrictions, I don't care if they're apples or pears. There are 8 pieces of fruit. And I want to know that this is the number of ways I could just pick out of 8 pieces of fruit, just picking 4 of them. So the top is me picking a particular situation, 2 apples and 2 pears. The bottom is me having 8 pieces of fruit and picking 4 of them. And see, again, you'll notice again in the second scenario, this is what I'm interested in. I'm interested in getting 3 apples and only 1 pear. That's this. But then I have to divide by 8 fruit, choosing 4. That's me selecting how many different ways I could select 4 pieces of fruit. Does that make sense? Yeah. And see, in this probability situation, again, you'll notice that this number, this number and this number are always going to add up to this number. And this number will always add up to this number. 6 and 2, 8. 4 and 0, 4. Okay, we're good with that? All right, now tell me about 6. What do we got to do here? So tell me what is this? What's 10? Nope, what's 10? That's exactly right. Well, these are my parameters. And again, if you want to think of it, parameters are important. The important numbers. In a binomial distribution, what are the important numbers? And that's what we're looking at. This is n, and this is p. Parameters, it just means the important numbers, okay? So, how do I find the expected value in a binomial distribution? Which is going to be 10 times 0.2. 10 times 0.2 is going to get me 2. That's how I find the expected value. How do I find the variance? What's Q? Exactly. Now keep in mind, what's N times P? So we could just do 2 times, and what's 1 minus 0.2? What's 2 times 0.8? That's going to be my variance. Okay? Now, in number 7, it says I roll 2 fair dice. How many throws would you expect to throw in order to get your first pair doubles? Now, is this about binomial or is this geometric? All right, because they refer to the first success, right? Now, what's the probability of getting doubles if I roll 2 dice? Exactly. What's 6 out of 36? No. Okay? Now, that's the probability of getting doubles. All right? Now, that's the probability of success. How do I find the expected value of a geometric distribution? Yeah, 1 divided by P. Okay? What's 1 divided by 1/6? It's going to be 6. Now, again, the nice thing about this is it kind of makes sense. If the probability of getting doubles is 1/6, doesn't it make sense theoretically that the first time you would get your first pair of doubles is on your 6th roll? Now, it doesn't mean, but that's how we find the expected value. 1 over the probability of success. Okay, good with that? And then take a look at B. The probability of getting at least 3 times, having to roll 3 times to get doubles. So again, probability of success is equal to 1/6. That's the only parameter for a geometric distribution. It's the only thing I need to know. Okay? Now, there's 2 formulas here. The probability that x is bigger than a number and the probability that x is less than or equal to a number. Do you remember what those are? So think about it. Basically what we're saying is that the probability at least 3 times. So what do I write? The probability that x is at least 3 times. Is it less than? Is it greater than? Is it greater than or equal to? What is it? Greater than or equal to what? All right, now the problem is that's not what this looks like. So what are the numbers that are greater than or equal to 3? And 3, right? How can I write this so it's x is greater than a number? Again, let's think about it. What are the numbers that are greater than or equal to 3? 3, 4, 5, 6, and on, right? How can I write this same exact thing, only make it say greater than, and still have these numbers be the answer? Exactly. Because it doesn't include the 2 then, doesn't it? What are numbers that are greater than 2? 3, 4, 5, 6, and on, right? So now we do this, and now we use that formula you talked about. It's going to be the probability of failure to the r. That's this, right? So what's probability of failure? To what power? So it's going to be 25 over 36. So you've got to make sure you memorize these. The probability that x is greater than a number is q to the r, or the failure to the r number. And then this is going to be 1 minus that. 1 minus q to the r. That's this. So tell me about number C. What does C say? All right, so first, is this binomial or geometric? Because why? All right, 10 trials. N equals 10. What do I want to find the probability of? So we want to find the probability of x equaling 3, probability of x equaling 4, and the probability of x equaling what? Right? Does this, if I find these probabilities, will that meet this? All right. How do I find the probability of it equaling 3? Remember, these two always have to add up to the same numbers, right? And then this is going to be and again, you're going to write this because this shows your method, but then you're going to go to the calculator. Where are you going to go? And then you're going to do binomial, that one at the very bottom, number 4. You're going to do a list. You're going to put in the numbers 3, 4, and 5. And then you're going to put in the probability, or I guess then it's going to ask you for n, and n is going to be 10. And the probability of a success is going to be 1/6. What's this first one? And then what's this one? And what's this one? And see, to find the answer to my question, all I got to do is add those up. Yeah, that's awesome. All right, last question. How many different ways can the letters Hopewell be arranged if there's no restrictions? How many letters do we got? How do I find out how to arrange them? So what's duplicated? Two L's. Anything else duplicated? Two E's. 8 factorial divided by 2 times 2. Now tell me about B. What's the probability of arranging the letters in Hopewell if there's an L on each end and the vowels are always together? All right, so we got 8 letters, right? But we're going to put our L's on each end. 1, 2, 3, 4, 5, 6, and then L. All right, these L's are always going to be there. They're never going to move. And they're identical, right? So I can even switch them and it doesn't change anything, right? So I'm not worried about these two L's. How many are in the middle? All right, now, what letters are not L's? All right, now we got to arrange those. We got to arrange them so the O's, oh wait, the vowels are all together, right? So here, let's do this again. Let's make this the P here and the O here. You with me on that? So we're going to do like what you did before. We're going to circle those. You with me? All right, now, that's the group that's staying together. So the first thing I'm going to do is figure out how many ways they can be arranged. How many ways can this group be arranged? Yeah. All right. That's the first thing that I do. Now, I think of it as being one group. So how many things do I have? 1, 2, 3, and 4. I'm not counting the L's because the L's are given. They're always going to be there. They're never going to switch, right? So 1, 2, 3, 4 things, yes? How many different ways can my 4 things be arranged? And are any of them duplicated? No, because keep in mind, yeah, we're considering this as one thing. So there could be duplicates in it, but there's only one thing. There's only one OEE, okay? So there's no double H's, there's no double P's, no WW's. So we just got to multiply those two things together. And that's going to give us a number of ways that this can work. All right, now, here's the trick, and here's what a lot of people missed. Is that what they asked? What'd they ask? All right, now this is the number of ways that will make me happy. This is the number of ways they can be arranged. So this is what I want on the top of my fraction, but what's the goes on the bottom of my fraction? And why is that? That's the number of ways the letters in Hopewell can be arranged if I don't care about anything. So this is what I got to do. This is the answer to the question. A lot of people just told me it was 72. But it's going to be 72 over 10,080. Okay? And then, is there more? Oh, here's this one, C. So here we're selecting letters from Hopewell. How many ways can 4 letters be selected if there's exactly one E in every selection? So let's start this. How many letters am I selecting? 1, 2, 3, 4. But there has to be an E. All right? Now, how many other letters are there besides E's? Or what are they? All right, so this poses a problem. When we're doing arrangements, if I've got duplicated letters, I just divide by the duplicates. But when I'm doing combinations, if I've got duplicates, I have to consider all the different scenarios. So here's the first scenario. Let's imagine first, is it possible for me to pick 3 more letters and have none of them be L's? All right, so the first thing is, I say to myself, what if there was no L's? So how many letters would I choose from? How many of them? How many do I have to choose from? And how many places am I going to fill? This is the number of ways I'm going to do this if I don't have any L's. Okay? Now, what if I only had one L? Well, see, now I've got an E, which I knew I was going to have, and then an L. Now what? How many non-L's do I have? But how many spaces do I have now? Okay? Now, is it possible for me to have 2 L's? So now there's only 1 spot left over. And how many letters could go there? But I'm only choosing 1. This is going to equal 4. This is going to equal 6. And this is going to equal 4 choose 3. What's 4 choose 3? 4. So, is there another way that I could have, because see now I've got no L's, 1 L, and 2 L's. Is it possible to have 3 L's? Because there aren't 3 L's. So these are all the possibilities, okay? When you're doing arrangements and you have duplicate items, like I said, you just divide by that number factorial. But the thing is, when you've got selections or combinations, if you've got a duplication, you've got to break it down into different scenarios where there are none of those duplicates, one of the duplicates, all the duplicates, until you get them all. Does that make sense? Any questions about that? Yeah. Because clearly, if you take a look at these problems, they all seem kind of similar, especially these letter ones with the permutations and combinations. You know, think about the different ways we're looking at it. These are the most common things you have to be able to do. You have to be able to find the number of arrangements when things are staying together. Like this one here. Okay? You have to be able to find a number of arrangements if things are separated. That's like this one here. You have to be able to find it whether there are things that are all unique, like in this case, everything was unique. And in this question, we did the same kinds of things where we found them together, but they were duplicates. And so we had to take consideration the duplicates. And then we have the other restriction of having these 2 L's on each end. As far as combinations go, sometimes we have multiple situations and we've got to consider all the different ways. Here, there's 1 bus and 1 car that we know are in there. And then here, we've got duplications. This is a common thing to run into where there's a duplicate. And see, what they would do is, in a case like this, they would tell you it has to have one E, because then it eliminates you having to figure out what happens with all the E's. By saying there has to be one E in every selection, well, now I don't have to worry about the fact that the E's are duplicated, because they're telling me there can only be one E, and it's already in there. So then I can deal with the L's. But the problem is that there are really some basic things you've got to do, but depending on the way they word the problem, they can seem really similar to each other. Yeah. And so the trick really is to do as many of them as you can, and even going back and doing ones that you've already done, but try to do it without looking and see if you can still do it. As far as the other part of the test, being able to differentiate between binomial and geometric distributions. Binomials are when they give you a set number of trials. Geometric is when we're interested in the first success, and only one success. You'll notice in a geometric, there's never more than one success. The question is, when does that one success happen? In a binomial distribution, there's very often, there could just be one success, there could be no successes, or there could be more than one success. In a binomial, I've got a certain number of trials, and what I'm figuring out is what's the probability of 10 out of these 12 trials being successful. And then as far as this probability distribution thing, this this table, this is a very common way to find probabilities. The other thing we did with the combinations, where we did the choosing, that's another very common way to find probabilities. These are two of the most common ways to find, different ways of finding probabilities. And there are more. But one of the things you have to be able to do is possibly build a probability distribution table. Cool? All right. So, you understand what's going on here? On Thursday, we're going to practice some more of this normal distribution. And then next Monday, we're taking a test over this stuff. It'll be normal distribution and then binomial. You'll notice in the problem you did today, what happens is the normal and the binomial sometimes get grouped together. And so, that's what the test, it's not going to be a lot of binomial, and there won't be any geometric, but it's possible that you'll see binomial and normal distribution questions together. So what's going to happen is that we're going to finish this chapter, and then we're going to take we're going to study, and we're going to take a mock, like a practice test, a statistics test. We're also going to study for the pure math. And basically what we're going to do when we're studying for the tests is we're going to be looking at old tests and old test questions. But really, after we get done with this chapter, that's what we're focused on. We're going to be focused on getting some review done. We're going to focus on studying for those tests. And like I said, we're going to take we're going to take a statistics test, and then we'll take a pure math test, and then you'll take your exams. Yep. Now's the time to step it up. And the thing is, everyone's getting tired. I can already tell people are starting to think about spring break. I know. We just got to kind of hang in there. You just got to kind of hang in there because, like I said, once we get past this, it'll be easy. Like I said, quite honestly, not a ton. What'll happen is that After a certain number of days, they'll give me the test. And so we may spend a class period and just go over the test and work out the problems so you can see how that goes. And maybe you can get a sense of how you did it or how you did do or whatever. And then you'll take the pure math test first. So we'll get that at some point. And maybe by the time you take in the stats test, maybe I'll get the pure math test back. And then it'll be a few days after you take the stats test. Then they'll give me a copy of the stats test, and we'll take a look at it. But no, quite honestly, we won't be doing too much. We just got to get through it. We just got to get to that point. Cool? What's that? No, we'll take it here. Oh, and that's what I was also telling the class today. Like, for example, I mean, this test that I just went over, this remediation, that's in the last quarter. And you know what? You've got a normal distribution test that's coming up. And you're going to focus on studying for the pure math test anyway. And if, for example, if you wanted to, like, if you want to retake this test next week, like after the normal distribution test, I mean, you're perfectly willing, I mean, I'm perfectly fine with you doing that. But if you also wanted to wait until after you took the exams, you could do that too. Because I'm going to have to put in a grade change anyway. So if you want to wait until after you take the exams and then retake this test if you want to, well, then you can do that. Right. And well, like I said, with this normal exam, this normal stuff, maybe you want to focus on it right now. But like I said, it doesn't make a difference to me. If you think it's better for you to wait, then you could wait. And if you want to get it out of the way, then you can do that too. But like I said, so the fact that we won't be doing much, you could be retaking this test if you wanted to. All right? All right, man. Well, thanks for coming. I got to get out of here. Have a great, great day. And we'll see you, on Thursday? Look on Canvas and it'll show you some of the problems we went over. Go to the lesson page and look at it and it'll show you the stuff. All right? Have a good one now. All right.